All right, CNT120, Chapter 4. We're going to talk a little bit of early Ethernet. When Ethernet started, it started off as a bus topology, and we hopefully talked about this before. This was the original Ethernet concept for Ethernet was a brainchild of Bob Metcalf. That's why I put his picture there. And his thought was, hey, if we have this central wire that we all connect to, this bus, and we tap into it, we can move data from computer to computer, if you will. And that was his early concept, his drawing for Ethernet. So the first Ethernet networks were just this big, thick piece of coax that the computers tapped into. And there was literally a transceiver. Transceiver is a fancy name for transmitter-receiver. It was a transceiver that bolted around, basically clamped around that coax cable. And this mechanism, this transceiver, there was actually a little screw with a spike on that would cut through the insulation, make contact with the copper wire inside to tap into the network, and affectionately became known as a vampire tap, because think of a vampire fang biting into the cable. Okay. This was the electrical connection into that coax bus, and all the computers were tapping into that. So that right there was the first Ethernet, and if I drew it conceptually, it was literally the computer tapping into this coax wire, this computer tapping into this coax wire, this computer tapping into this coax wire. So I could draw my network like so, showing this is how it's logically connected together. Physically like that, but logically like this down here. As Ethernet advanced, they started using thinner coax. This was some of the first coax networks that I hooked up, these guys right here. These were using thinner coax with these little T connectors. So I didn't have these taps to clamp around. You didn't have these taps to clamp around, but you had these little T connectors that would screw on and lock onto the NIC on your computer, and then the cables would connect so. The connection was different. However, logically it's still connected like so. That was your first Ethernet. So as I move to a picture like this is just a logical representation of what was really there. There is nothing here. There is nothing on this wire to act as like a traffic cop, if you will. It literally is a wire that everybody's connected to. So as data on this computer gets sent into the wire, it literally gets sent to everybody. There's nothing to say go here, go there. It's going to everybody. So in this environment, when this computer went to send, it goes to everybody. And while this computer is sending, everybody else waits until they're done. That's just how the network functioned. So if I put it into a flow chart or a flow graph, if you will, of how this was working, well, Ethernet worked in this manner. It was using CSMA CD, carrier sense multiple access with collision detect. Carrier sense multiple access with collision detect. That is what Ethernet was using. And it worked in this manner. Again, I'm not a big flowchart kind of guy. However, this does a great job of showing how it worked. A computer would listen to see if there was any data moving by on the network. If it detected any data moving by, it's going to wait. Listen for activity, detect it, wait. So it literally is going to wait until there's no data moving by on the network. Once it senses no data moving by, boom, it transmits. You notice there's nothing fancy here like wait 5 seconds or check with a neighbor or, do this special thing. It's like, no, once I hear no activity on the network, boom, I'm going to send my data. As I like to make the joke, this is kind of like getting on the highway, getting on like Interstate 81. When you see a gap there, you kind of mash the gas and go, man. If you don't, people behind you are going to hit you or go around you on the berm or something like that. So this is very much like getting on the highway. When you see a brake, boom, you mash the gas and you go. So here, I'm sensing if the network is busy. All of us are connected to the same network. That's the carrier sense multiple access. And when I go to send, I'm listening for activity. When I hear none, boom, I send. Now, once I send, I'm going to continue to listen. And this is the collision detect part right here. I'm going to continue to listen for any problems. If I don't hear any problems, if I don't hear any collisions, I'm going to assume the data got there, the transmission complete. I'm going to assume the data got there. There's no double check. There's no message that comes back to say everything's okay, giant thumbs up. That doesn't occur. I'm going to assume the data got there. If I do hear a collision, crunch, okay, hopefully you have not heard two cars collide, but if you do, you can imagine the whole, crunch, the two cars crunching together. The same kind of thing happens in your data network. When those two data frames, commingle, if you will, all of a sudden you start having spikes in electricity. So when you detect a collision, and again, all of these would hear it, I'm using little air quotes now, you would hear that. So you're going to stop transmitting. A jam signal goes out to say, hey, we got a collision. And what that does, it tells everybody to stop doing whatever you're doing. Everybody waits a brief time. Now, it actually worked as a back-off algorithm. Everybody waited a random time is what it amounted to. Everybody waits a little random time, and then they start over to be like, okay, I'm going to listen for traffic. I hear it. I'm going to wait. I hear none. I'm going to send. This is how traditional Ethernet worked. Excuse me. That is your CSMA CD, your traditional Ethernet networking. Now, as we got away from the coax bus and we started using twisted pair cabling and hooking everything up to this central connectivity device, that initial connectivity device was a hub. Hub is a layer 1 device, and it's designed to repeat everything. So in this case, again, computer A here goes to send data. When it hits the hub, it literally repeats to everybody. And the intended recipient gets it, but everybody else gets a copy too. So this layer 1 hub is functioning the same way as my coax bus. That layer 1 hub is functioning the same as this coax bus. So initially, this didn't function any different with this hub in here. What it gave me was there was an individual connection for every computer. So this connection here, if it failed, it didn't affect anybody. Back on the coax bus, if this connection failed, it could affect everybody. Okay, so these individual connections now make it a little bit better that if I have a failure here, it doesn't affect anybody else. I also start getting little link lights here. That lets me know that it's plugged in and working or not plugged in and working. We didn't have little blinky link lights out here. That didn't occur. So this is actually helping me with everybody gets an individual connection. I get a blinky link light. It makes it easier to hook up and disconnect. As I add people to the network or take them out, it doesn't affect anybody. Whereas back here in this coax bus, if I disconnect this guy or plug him in, it affects everybody. I just kind of broke the network in half. Okay, so this is adding some admin side, but functionally it's working the same as this coax bus. Okay, so a lot of people see that and it's like, well, why did we do that? Well, we're getting the little blinky link lights and individual connections, all that good stuff. It's not until, and here's an example of a hub, when one goes to send to two, it literally goes to everybody. It really goes to everybody. Well, once we started using switches, and for a lot of people that was early 2000s, late 90s, I knew of places like, Navy depots and so forth that were starting to put switches everywhere. So a lot of businesses were doing it early 2000s. That was some of the first places that I knew doing it. Well, with the switch now, the switch is layer 2. It actually tries to learn the MAC address of anything attached to any port. And the idea now is when data comes into the switch, it goes, hold on. I know where that MAC address is, and it tries to send it out one and only one port to that specific node. So with a switch, I now have a scenario where while one goes to send to 2, it's not sending anybody else, I can actually have 3 send to 4. I can have 2 conversations going on at once, so to speak. I can have more than that, but it actually tries to send data to just one node, and because it's doing that, I can have multiple nodes communicating individually in their little sessions. That is what our switch added to our network. Everything else looks the same, but functionally, I got rid of some of this collision nonsense. So that brings up the whole collision domain, broadcast domain thing. When I had the whole hub network, or the coax bus network, everything was part of one giant collision domain. Everybody was part of this giant area where collision could occur. Two computers could be sending data at the same time. So in this coax bus days or the hub days, all of these belong to the same collision domain. Well, what that means is, if I get down to the nuts and bolts, this is an area where collisions could occur. So this is an area where we share the bandwidth. All of these nodes, all these devices are sharing the bandwidth that's here, because while I'm sending, you wait. While you're sending, I wait. So this whole idea of all of us belonging to one collision domain means we all are sharing the bandwidth. And that's not a good thing. If I put a switch in, something layer 2 or higher, this now breaks it down that less things are competing for the bandwidth. So with a layer 2 device in here, let me go to this picture here. Here this hub is showing everybody shares, that is one giant collision domain, everybody's sharing there. But if I go to a switch, each one of these is going to be doing their own data, so I won't have collisions with anybody. So each one of these is going to get its full bandwidth. I'm not sharing with anybody. The hub was sharing. We're all sharing that bandwidth. Here, I'm getting, each one of these is getting their own full bandwidth, if you will. So having one big collision domain where all those people are sharing, these little teeny small ones that the switch is doing, we're not sharing bandwidth anymore. So that's a good thing. Putting that switch in gets rid of this whole collision domain problem and creates many, 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 many small ones where collisions can't occur. The other concept to think about is a broadcast domain. And that's an area where a broadcast can occur, like ARP, like we looked at earlier. Some protocols are going to broadcast by default. So putting in a router, layer 3 router or firewall, these do not pass broadcasts. They're going to filter. They're not going to, they're doing broadcast control. They're not going to let broadcast propagate. So something layer 3 or higher, or VLANs, virtual LANs, they're going to stop those broadcasts. So right here, this router is going to keep these broadcasts maybe at this floor or this site. This router is going to keep these broadcasts at this floor or this site. And that's good. I do need to contain them because, as we saw, ARP occurs. It occurs. So at some point, I need a boundary to contain this stuff. And things like routers, firewalls, and VLANs are going to do that. So there is some of my legacy networking, mainly the CSMA CD part of Ethernet. And as we saw kind of the evolution here from the initial concepts into using hubs and switches, you now see with switches now we're getting this individual connection. We're getting, like full bandwidth to everything. This whole CSMA CD and the collision thing kind of goes out the window because of what we're using now and the intelligence of the device we're using.